Hello everyone, my name is SOMYA GUPTA and I am currently in CSE branch second year student from Bangalore Institute of Technology, and today I'll be talking about realization of MUX or realization of multiplexer. So, the various topics that I'll be covering under this are what is multiplexer. We'll be learning what are the various types of multiplexer, and we'll be going in details about 2 cross 1 multiplexer, 4 cross 1 multiplexer, and 8 cross 1 multiplexer. Also, we'll be seeing how to implement 8 cross 1 multiplexer using 4 cross 1 and 2 cross 1 multiplexer. We'll also be seeing how to realize logic expression using multiplexer, and in the end I'll be telling about one of the applications of multiplexer, that is how to realize basic gates using multiplexer. So, moving on, firstly, what is multiplexer? So, the multiplexer, shortened to MUX or MPX, is a combinational logic circuit designed to switch one of the several input lines through to a single common output line by the application of a control signal. So basically, what it is saying over here is the number of input lines are more than one over here. So we can take the number of input lines as n, and the output is always one in a multiplexer, that you should always remember. And by the application of a control signal we can also say, we can also call them as selection lines. So we can take the number of selection lines as m. So n are the number of input lines, one output we'll be having, and m control signals or m select lines. Now, moving on to the various types of multiplexer. Firstly, we'll have 2 cross 1 multiplexer. So, as it is very clear from the name, 2 cross 1 means we'll be having two inputs and one output. Multiplexer will definitely have one output, so that is not at all confusing. And since 2 cross 1, so n will be 2 over here. What is n? N is the number of input lines. So, we'll take n as 2 and 1 as the number of output lines, and m, as I already told before, m is the control signals or the number of selection lines. So here we have one formula: 2 to the power m is equals to n. M here is the number of selection lines and n is the number of input lines over here. So we have n over here as 2, so it will become 2 to the power m is equals to 2. So we can see m over here is 1. So we'll be having one selection line, that is S naught, and single output, as I already told before. So on the basis of combination of inputs which are present at the selection line S naught, one of these two inputs will be connected to the output. So in multiplexer, always either A1 would be the output or A naught would be the output. So it basically depends on the input of the selection lines. It could be either 0 or 1. So depending on that, the output would either be A naught or A1. It would be A naught if our selection line is 0, and it will be A1 if our selection line is 1. So you can see this is the selection line and this is the output. I already told, if it is 0, then our output is A naught, and if it is 1, the output is A1. We can frame this logical expression with the help of this truth table itself. So we'll have, since it is 0 over here, we have to take bar. So it will be S naught bar into A naught plus S naught into A1. So we'll get the expression over here: y is equals to S naught bar into A naught plus S naught into A1. Now, moving on to one of the most important parts of this multiplexer, the logical circuit. How to form make logical circuit? We can do it really easily using this logical expression: y is equals to S naught bar A naught plus S naught into A1. Since we have a bar over here, we'll have to take a NOT gate. So here we'll take S, and for S naught bar we have to take a NOT gate. So here comes S naught bar and A naught. Now, since in this second term we don't have a bar over here, so we'll directly take it as S naught. So here the inputs would be S naught, and here the input would be A1. And since these are the AND gates, we very well know the output for AND gates are always in multiplication, that is A naught into S naught bar, and here it will be A1 into S naught. And final expression, this is our OR gate, and for OR gate we add the two terms. Okay. Now moving on to our next type of multiplexer, that is 4 cross 1 multiplexer. So in 4 cross 1 multiplexer, there is a total of 4 inputs, since it's visible over here, and that is A0, A1, A2, and A3, and two selection lines. How we'll find selection lines over here? 2 to the power m is equals to n. So n over here is 4, so we'll get it as 2 to the power m is equals to 4. So m would be 2. Since it will be 2 to the power 2, so m will be 2. So we'll have two selection lines over here, that is S0 and S1, and a single output since it's a multiplexer. So, on the basis of the combination of inputs that are present at the selection lines S0 and S1, one of these four inputs are connected to the output. So, basically, depending upon here, since there are two selection lines, so it won't depend on one, it would depend on the combination of these two. The output would either be A3 or A2 or A1 or A0. So, depending on the combination, the output would be one of these. Okay. Now moving on to its truth table. Since there are two select lines, we can have a combination of four. So combination of four inputs to be precise, and the output would be A0, A1, A2, A3, depending upon this. And the logical expression, we can again find out the logical expression easily using this truth table. Since S1 is 0 over here, we'll write S1 bar into S0 bar into A0 plus S1 bar into S0 into A1 plus S1 into S0 bar into A2 plus S1 S0 into A3. So this is very easy, I guess. We can reduce this logical expression. Now, how to draw the logical circuit of the above expression? So again, we'll do the same thing. Wherever there is bar, we'll take a NOT gate, and where there is no bar, we won't take a NOT gate. So we can easily draw, since this is S1 and a NOT gate, it will come as S1 bar, and similarly, we'll have for S0 also we'll have a NOT gate wherever required. Okay, so we can easily make this logical expression. Now, same goes for 8 to 1 multiplexer, 8 inputs, and for select lines, we'll see 2 to the power m is equals to 8, and obviously 8 is 2 to the power 3, that is 2 cubes, so n will be 3 over here, and the number of select lines m would be 3 over here, so the number of select lines would be 3. Now, since the number of select lines are 3 over here, we'll have the combination of 3. So for 3, we always have 8 combinations over here. That is from 0 to 7. Now this is what this I can write it in decimals, and this is their binary representation. So now seeing the block diagram. Wait, first I should read all of this. On the basis of the combination of inputs that are present at the selection lines S0, S1, S2, one of the 8 inputs are connected to the output. The block diagram and truth table are given below. So again, as I told, depending upon this combination, we'll get one among these 8 inputs. So if the combination says it is 0, then we'll get output as A0, similarly 1, A1, 2, A2, and so on. Logical expression, again, we can find out using this truth table. So wherever it is 0, we'll again take it as bar, and wherever it is 1, we'll leave it as it is. So we'll we can get this logical expression. Now this logical circuit, it might be looking very difficult, but trust me, this is very easy. And Here, what it is like this, that we have provided S2 over here, and we have provided a NOR gate over here, so that we can get S2 bar. So for wherever we require S2, we'll take it as it is, and wherever we require its complement, we'll take a NOT gate. And similarly, same thing goes for S1, S and S naught. Okay. Now how to implement 8 cross 1 multiplexer using 4 cross 1 and 2 cross 1 multiplexer. So we can implement this using a lower order multiplexer. Obviously 8 cross 1 is a higher order multiplexer, and to implement this we need two 4 cross 1 multiplexers and one 2 cross 1 multiplexer. The 4 cross 1 multiplexer has two selection lines, as we already saw before, and four inputs and one output. Now the 2 cross 1 multiplexer has only one selection line. This we've already seen in the beginning of this. Now for getting 8 data inputs, we need two 4 cross 1 multiplexers. The 4 cross 1 multiplexer produces one output. So in order to get the final output, we need a 2 cross 1 multiplexer. The block diagram of 8 cross 1 multiplexer using 4 cross 1 and 2 cross 1 MUX are shown below. So as we already saw, we'll be using two 4 cross 1 multiplexers. Since we have 8 inputs, so 4 in one and 4 in the other, and selection lines for 4 cross 1 multiplexer is always 2, so we'll have two selection lines over here. And since multiplexer has always one output, we'll get one output uh, all from both of them, and we'll again be passing it to 2 cross 1 multiplexer. Okay. Now, realization of logic expression using multiplexer. Now, for logic function realization, instead of logic gates, multiplexers can also be used. Consider a Boolean expression, f is equals to 1, 2, 6, 7. Here, input variables could be taken as a, b, and c. So wherever now how to realize this using MUX, wherever it is 1, 2, 6, 7, we'll connect it to VCC, that is 1, and the rest of them to ground. Now, depending on the control input combination, specific input is connected to the single output of the multiplexer. So we can have this logical expression again, as I already told before. Now, when multiplexer is used to implement the above function, we connect Boolean logic 1 at the inputs corresponding to control inputs A, B, C. Now, for all the input Boolean logic, 0 is connected. 0 is ground for us. It is given as GND in the circuit. And in case we take a multiplexer, we make as control input and then determine what should be connected at the inputs of the multiplexer as shown below. Now, we'll from that from the expression we have over here, we can find out BC. And for that BC, that is, in this, what we do, we take two, we'll be having three inputs. We'll take two inputs, and the third input we'll be taking it so that we can get an output. So we'll be getting an output like this, and we can realize this we are realizing 8 cross 1 using 4 cross 1. So when we are getting this, wherever it is 0, we'll connect it to ground. Wherever it is 1, we'll connect it to VCC. And we, for A and A bar, we can again have A as an input, and then the for bar we can have a NOT gate. Now we can also the applications one of the application of this is we can implement NOT gate, AND gate, and OR gate using multiplexer. Now we just need to remember over here is that we'll have 1 and 0 as our input for NOT gate. For OR gate, AND gate, we'll have input as 0 and y, and for OR gate we'll have input as y and 1. So these were one of the applications of multiplexer. So I'll be ending it over here. Thank you so much. Thanks for watching.